All right, in Chapter 5, we're dealing with chemical reactions now. And an important thing that drives chemical reactions is the concept of free energy. By the way, the title Free Energy, and especially Section 2, which is titled Free Energy as a Force Towards Equilibrium, always makes it sound like some kind of a hippie manifesto. But it's free energy is, we're drawing on the idea of enthalpy, starting with enthalpy, and we're applying it to other situations. In fact, recall that enthalpy is H defined as the system's energy minus PV. Oops, plus PV. Gotta get those signs right. And we're assuming when we use this that pressure is constant. Now, remember how we defined what enthalpy, how we interpreted what enthalpy meant. The system's energy plus some constant pressure environment and the change in volume, or the volume it takes up. Enthalpy is basically what energy you'd be able to get back if you took your system. The book has this very cute picture of a magician making a rabbit vanish. Well, if a rabbit vanished, what energy would you get out from it? Because all energy you can't create or destroy energy. And remember that mass is simply a form of energy, E equals mc squared. If you made a rabbit vanish, what energy would you get out of it? Well, if you're off in the vacuum of outer space, you could convert all of its atoms into a flash of light, pure energy, and you would get out the energy equivalent of the matter contained in that system. And that's it. But if you do that here on the Earth with a constant pressure atmosphere surrounding it, the rabbit took up space. That space that couldn't be occupied by the atmosphere. So, when you make the rabbit vanish, flash of the magic wand, this is a very small magic wand, you would have not only the flash of light there would be a popping sound as the air rushed into the vacuum that was created. There would be work done by the surrounding atmosphere on the space left by the system. And in principle, you could put a piston there, a cylinder, and you could drive and you could recover that. The atmosphere expanding into that space could do work that you could recover as well. So there's the energy of the system plus the work done by the environment at constant pressure, we're presuming, as it rushes into that volume occupied by your system. So you actually get a bit of extra energy because your system took up space. Well, if you're going to create the system from scratch, really from scratch, I've got a whole lot of light here. You can actually turn, we do it in particle accelerators occasionally, collide two photons head on, and they can actually turn into matter. For example, electron-positron pairs, things like this. So let's say you've got a whole lot of just pure energy. You turn it into matter. Well, the matter has to take up space by definition of what matter is. So you turn it into matter. What you've got, if you're doing it in the laboratory here, there's an atmosphere around it. You can't have the atmosphere here and a rabbit sitting here at the same time. You've got to push the air out of the way. So you have to do work on the atmosphere to slip your system into place. So it costs you an amount PV there to make room for your system. In addition to the amount of energy you had to put in to make your system to have its own energy. So even if you're doing something gradually, let's say you're assembling a system just atom by atom there. Well, as it grows in, it takes up more and more volume, and so you're still doing work in moving the atmosphere out of the way. Assuming you got the atoms from somewhere where they weren't taking up space, I guess. The expansion when we did the steam engine. Water boiling into steam takes up more room. So there's work done in pushing the atmosphere out of the way as it does that. So that's why we were using enthalpy. in there. We had water boiling at constant pressure. Went from taking up a very small space as water to a very large volume as steam. Okay, but this is what's useful for us if we're in a constant pressure environment, but we can also have some energy that we get free, that we can recover free of charge if we are in a constant temperature environment, and that's another common situation. So, let's see here. So if I'm reading from the book at this point, sometimes if the environment is one of constant temperature, the system can extract heat from the environment for free. So all we would need to provide to make the system is the additional work needed to move it into place. And when we annihilate the system, we vaporize it, then we can't really recover all of its energy as work because its entropy has to go somewhere. You can't destroy entropy. And so that would be eliminated by dumping some waste heat into the environment that was stored in the system. So, we're going to define the Helmholtz free energy in the situation of a constant temperature environment. Okay. So, F for free. The free energy, F, is defined as U minus Ts, where T is constant, or it's useful to us in a constant temperature environment. So this is the total energy needed to create the system from nothing minus the amount of heat, Ts, that you can get for free from the environment surrounding it that's in thermal contact. It will flow into it when the environment is at a constant temperature, T. So how are we interpreting this as heat here? Recall that for a quasi-static process, Q equals TdS. This is something you already knew. For macroscopic change, then, for macroscopic flow of heat and macroscopic change in entropy, that'll become Q equals T delta S. So that's final entropy of the system minus the initial entropy. The final entropy is just going to be S, we'll call it that. The initial entropy of the system, if we're making it from nothing, is 0. We start off with no system, so we start off with no entropy in the system. So that means the amount of heat that flows into the system from the environment, from an environment at constant temperature T, is Ts. Okay. Now, if we annihilate the system, then, let's see here, the energy that comes out as work is F, because it's the system's total energy minus the amount of heat, the energy that flows away into the environment in the form of heat when we do that. So the idea of F being the free energy is really when we're interpreting it as how much we're able to extract by annihilating the system in whatever way that would be. We can't get all of it back because some of it flows away in the form of heat into the environment. After all, you can't destroy entropy on there. And come to think of it, this really gets into one of the deep mysteries of cosmology and relativity and quantum mechanics, with the idea of entropy loss or not from black holes, or into black holes. But that's a topic for another time. We know what, though? This works well when we're at constant temperature. Okay, the surrounding environment in this room is at room temperature. Actually, it's somewhat below room temperature. I'm shivering slightly up here. But we're also at constant pressure. There. Well, if you're in the laboratory and you've got some chemicals in the beakers here, you're working on them, you've often got a constant temperature, and if they're open to the environment, you've also got a constant pressure. They're in thermal contact, more or less, and they are they're open, so they've got that, they're in mechanical contact, we could say. Well, what if we've got to account for both constant temperature and constant pressure? In that case, we define what's called the Gibbs free energy. Yeah, that's it here. G for Gibbs. Unsurprisingly, it is the system's energy, U, minus Ts plus PV, where T and S both are constant. Sorry, T and P are both constant. All right, so this is a case where G is the amount of work we need to do to create the system, or the amount of work we can recover when we destroy it is the Gibbs free energy then. All right. So again, Ts gives us the amount of energy that flows away from the system as heat if we're destroying it again. And PV is the amount of work that we can, work that's done as the air rushes back in to occupy the space. So we recover the system's internal energy minus some that, that's some of the heat that flows away because we've got to dump the energy somewhere. But we also get out positive the work done by the atmosphere on that vacuum that's left behind. Incidentally, in the Harry Potter books, when somebody disappears from somewhere or appears somewhere, there's this popping sound that's never really described. PV. That's actually something that's physically correct that has to be done, even in a book describing a waving the magic wand. Okay. So, boy, we've got energy, U. We've got the enthalpy, H. We've got free energy, F. And we've got the Gibbs free energy, G. All of these are in terms of energy. These, in fact, are called thermodynamic potentials. And there's a relationship between them. Down to the last, that could otherwise give piece of chalk there. There's a nice grid here. Probably every textbook has some version of this. My graduate book, in fact, had almost the same diagram here. Okay. Trying to think of where I can write the phrase thermodynamic potentials. There we go. So, these four are related as follows. Start off with the system's energy, U. And if you subtract the heat that flows out when you annihilate the system, so minus Ts for anything that's to the right of this column here. If you are adding the work done by the air rushing back into the vacuum when you annihilate it, then you have plus PV going down that way. Make sure I've got PV in that. So, this means that F is U minus TS. Actually, I should write this over a little to the right. And that a little farther down. That'll make it clearer. Which way F is minus TS. There we go. So U minus TS is F, the Helmholtz free energy. U plus PV is H, the enthalpy. And U minus TS and plus PV is G, the Gibbs free energy. All right, so it's a nice way of remembering those there. Thermodynamic potential. So why do we use the term potentials for these? It brings to mind potential energy. Well, there's a reason that these actually behave in much the way of potential energy. Remember that one of the features of potential energy is energy that can be, in classical mechanics, potential energy is the energy that can be turned into kinetic energy, energy of motion. Well, it's stored up in the system in a way. And that's similar to what's going on here. The system, by virtue of having some temperature and having some volume, contains some extra energy that we might not otherwise be aware of. But when we destroy it, we're able to extract some of that back. And we had to put it into it in order to create the system in the state that it's in. So there's potential energies in classical mechanics always are with reference to some reference point. What's the potential energy of this due to gravity? Well, the higher up it goes, the more potential energy it's got. But where does it have zero potential energy? I could say when it's resting on the chalkboard here, then it's got zero potential energy. And I can measure its potential energy as I go up from there, some positive amount above zero. And for that matter, it can have negative potential energy when it's down below this. Negative is always fine. But I could have chosen the floor to be the 0 point. Or I could choose the center of the Earth, or the center of the galaxy, or here it could be the 0 point, or whatever. All of those will work just fine, because we're always concerned about a change of potential energy, so the 0 point is arbitrary. A similar thing goes on with thermodynamic potentials. How much energy does the system really have, U, there? Well, chemical reactions, we are rarely, actually in a truly chemical reaction, we are never really annihilating the system and turning its matter into energy. We're never, those are quantum mechanical or nuclear processes that can do that, and more high energy particle physics and things like that. Chemistry, we're really just bonding and unbonding things for the most part. So the matter, the mass energy contained in it, that's actually a lot of energy. I mean, if you had just a handful of antimatter and you threw it into the room, you would get a gigantic citywide explosion from just a little bit of mass there. So really, we're not really concerned about that total amount there. So we might really only worry about its, if it were cold and in its most elemental state, you look things up in that table in the back of the book. And that might be more useful. But really, when we're dealing with changes in G, or changes in F, or changes in H, changes in U, well, we might not even need to decide on what our reference point is, because the change will be irrespective of where the 0 point is. Delta G, you can have any 0 point you want and you'll get the same change in G. Okay. So, let me apply some of this here then. Consequences of these. If we want to deal with the Helmholtz free energy F, again, some of these Helmholtz, now there's H which is not the Helmholtz free energy, it's the enthalpy. There's the Helmholtz free energy is F for free. Then there's the Gibbs free energy, which is G for Gibbs. So it's not like they knew all of these by the time they named them. You kind of hunt and peck and find your way along. So the letters are a little inconsistent. Okay. If we have a system that goes through a change at constant temperature, T, then the change in F is going to be, well, F is U minus Ts. Where T is constant. So a change in F at constant T is going to be delta U minus delta Tx, but T is constant, so I can pull it outside that delta operator. So it's T delta S. And if you're a little unsure of why you're able to do it like this, when you've got a function which is the sum of other functions, sum of differences, if you just write F final minus F initial equals U, U final minus U initial minus T final, S final plus T initial, S initial, and you rearrange the terms and group them, you'll get exactly this. All right, but I'm just going to skip the algebra. Okay, so if I've got constant temperature, I can use the Helmholtz free energy. It'll be useful. Now, I've got delta U and I've got T delta S. First of all, delta, let's see, T delta S. First of all, the first law of thermodynamics, delta U is Q plus W. And we're going back, after that chapter on engines, we're now going back to our normal definition of work as the work done on the system, not by the system. So first law, Q plus W. So that's Q plus W minus T delta S. T delta S, well, we see that assigned to heat before, but we've got to be careful. If no new entropy is created during the process, then Q equals T delta S. Okay, under those conditions, delta F would be equal to the work done by the system. That would cancel out with this here. But if there is new entropy created, then the heat flow will be less than T delta S. That is, there is more entropy coming in than just from the what there is by the heat flow then. Okay, which would mean that, let's see, if there's no new entropy created, F would be equal to W, and if there is new entropy created, that is less than the magnitude, let's see, Q is less than T delta S, and so F would be less than W in this case. So we can conclude that in general, these were both delta Fs. There we go. In general, the change in the Helmholtz free energy is less than or equal to the work done on the system. And this is all work. It's not merely mechanical work. Every kind of work there. All right. At constant temperature. Remember, if you're at constant temperature, Helmholtz free energy is the one that you want to go with to analyze the system. Now, what if we've got a system at constant pressure and constant temperature? We've already dealt with the enthalpy. where we were dealing with only constant pressure, no regard to temperature. Now let's see if we've got both constant temperature and constant pressure. So, the Gibbs free energy is U minus Ts plus PV. So, at constant temperature and pressure, delta G is delta U minus T is constant, so T delta S, P is constant, so plus P delta V. Okay. First law of thermodynamics. Delta U is Q plus W. Put that in here for delta U. So I'm going to rearrange the terms. So Q minus T delta S plus W plus P delta V. Now, we've already, just as before, if there's no new entropy created, Q equals T delta S. If there is new entropy created, Q is less than T delta S. So, let's recall then that Q in general is less than or equal to T delta S. Now, what about the work and P delta V? Okay, because work equals mechanical work plus other kinds of work, electrical work or whatever else like that. And the mechanical work then, at constant pressure, is negative P delta V. Then, this W plus P delta V is going to be either, if there's no other work done, only mechanical, then this term is these two terms add up to 0. If there is other work, these two will be greater than 0. So then, in general, let's see. Now wait, with my signs there, I may have that backwards. I'm not going to try writing it that way because I'm just confusing myself with the signs. But nevertheless, the two of these together will either be 0 or greater than 0. All right, that's a good way of putting it. All right. So, this all comes down to negative, and that's that. All right. Therefore, the change in the Gibbs free energy will always be less than or equal to this last term we've got left out here that hasn't canceled out. The other, it'll be less than or equal to the other kinds, the non-mechanical kinds of work done. And the reason it could be less than, well, we've got these two terms here where this could be some positive number. If Q is less than T delta S, then there is something positive left over here. And if there is other work, then we have something positive left over here. Right, okay. So we have that there is the limit. Okay. So what is the useful thing then? in order to use this in a problem, to find out what's going on, what's driving the system, second section is going to get us towards how we get chemical equilibrium in the system. Like if you've got a reaction in principle can go either like hydrogen and oxygen can combine to form water, or water can dissociate to form hydrogen and oxygen. And in general, both things are happening. Well, which way does your system go? Is you'll always have a few free hydrogen and free oxygen atoms, and you'll always have some water droplets in any system there. But where is the equilibrium? What fraction are associated and what fraction are combined into the molecule? And that's going to be driven by free energy. Okay. So in order to find out what's going on in the system, in practice, since delta G or G in delta G is so useful then, you've got tables of this. In order to calculate it, first, you measure, well, let's see, actually, I should present it that way. The book kind of does this backward, but I've redone it on my notes. Okay, just as before, delta G is delta U minus T delta S plus P delta V, just as I derived a minute ago. Recall that the enthalpy, H, is U plus PV. See, I've written it incorrectly on my notes, but I concluded correctly. All right. Should have known that. Delta H is U plus P delta V. So delta U plus P delta V. So it is the combination of the first term and the third one. So if we write it in terms of the change in enthalpy, it's the change in enthalpy minus the extra term, T delta S. So that is a practical way of using delta G or calculating it, because it puts delta G, the change in the Gibbs free energy, which is a big thing that drives these reactions, into change in enthalpy, and we have tables of enthalpies, and the change in entropy for the system, which you can get from tables. The two of those, you can actually calculate the change in entropy. And so this is the practical way of getting the change in Gibbs free energy for the system. Okay. And I think I'll end up here. I won't go over the example for it until the next class. But we'll apply this and find out how much, when there is a chemical reaction, how much does the system's Gibbs free energy change? And then we'll find out how does that, well, one, that will allow us to figure out how much energy we can extract from a reaction, or how much energy we've got to put into it to make the reaction happen. This is the application they give are in batteries, fuel cells, things like this, where we get actual electricity out. And then we'll look and see how we can figure out the equilibrium situation for some system. It'll keep reacting until we get to a point where there is no net change in the Gibbs free energy.